Introduction to Quantum Information Processing. Welcome to Lecture 6. In this lecture, we are going to see some simple quantum algorithms in a framework called the black box model. We'll specifically see quantum algorithms for Deutsch's problem, the 1 out of 4 search problem, and the constant versus balanced problem. Imagine that f is some function that is unknown to us, and we're given a black box for f, which is a device that enables us to evaluate f on any particular input of our choosing. If we want to evaluate the function on some input x, we insert x into the black box, and then the value of f of x pops out for us to see. We call this process of evaluating the function at an input a query. Assume that that's the only way that we are allowed to acquire information about the function f. Now, suppose that we want to acquire some information about a function f, and that we want to do this with as few queries as possible. It's kind of like a game, where we want to know something about an unknown function f, and we're only allowed to ask questions like, what's the value of f at point x for any x of our choosing? How many questions do we have to ask? An example of this from a topic that you might find familiar is polynomial interpolation, where one is given a black box computing an unknown polynomial of degree d, and the goal is to determine which polynomial it is. For example, suppose that f is a linear function over the real numbers, but we don't know which linear function it is. At how many points do we have to evaluate f to figure out which linear function it is? Evaluating f at just one point is not sufficient, but evaluating at any two distinct points is sufficient. And if f is quadratic, then 3 evaluations are necessary and sufficient. In general, if f is a degree d polynomial, then the number of queries that are necessary and sufficient to interpolate the polynomial is d plus 1. We're going to consider problems like this, but for functions over binary strings. The first problem that we'll consider involves functions that map 1 bit to 1 bit. In fact, there are 4 such functions, and here are the truth tables of each of them. The first function is 0 everywhere. For any input bit, the output bit is 0. The second function is 1 everywhere. The third function is essentially the identity function. Input x results in output x. The fourth function is essentially a NOT operation. 0 gets mapped to 1, and 1 gets mapped to 0. Imagine that we're given a black box for such a function, but we don't know which of the 4 functions it is. Now, suppose that our goal is to determine whether or not f of 0 equals f of 1. Thus, we want to distinguish between these 2 cases. One case is the case where f of 0 equals f of 1, equivalently where the XOR of f0 and f at 1 is 0. The other case is where f of 0 is not equal to f of 1, which is the case where the XOR of f of 0 and f of 1 is 1. How many queries to f do we need to accomplish this? Now, please pause the video until you have an answer. Okay, is your answer 2? The point is that 1 query is not enough. For example, suppose you made a query at 0 and determined the value of f at 0. Then f of 1 could be the same value, or it could be a different value. So you don't know which case you're in based on just knowing f of 0. How many queries do we need for a quantum method? Well, to address this, we need to know what is meant by a quantum method. Is there such thing as a quantum query? The classical query maps bits to bits. Define a quantum query so as to map the corresponding computational basis states to computational basis states. So here are the 4 possible functions again. And here would be the corresponding mappings on computational basis states. By linearity, we get these 4 linear operators. The second 2 are familiar unitary operations, the identity operation and the poly-X operation. But notice that the first 2 are not unitary operations. This is a serious problem. Violating the unitarity rule has consequences. For example, the first 2 linear operators, they both map the ket minus state to the 0 vector. That is, the 2-dimensional vector whose amplitudes are both 0. Such an output clearly makes no sense as a quantum state. So that didn't work out. A classical operation from bits to bits can only be quantized in this manner if it is bijective, in which case the matrix will be unitary. We will redefine our notion of what a classical query is in order for it to be quantizable. That is, so that the corresponding mapping on computational basis states is unitary. Here's a new definition of a classical query. Note that f is still a function from 1 bit to 1 bit, even though this overall operation is from 2 bits to 2 bits. For any input bits, a and b, the output bits are a and b XOR f of a. So this resembles a C0 gate for which the second bit is flipped if and only if the first bit is 1. But here, the second bit is flipped if and only if f of the first bit is 1. It's easy to see that this 2-bit operation is a bijection, whether or not f itself is a bijection. One way to see this is to think about what the inverse mapping is. Based on classical queries in this form, we can now define quantum queries in this manner for computational basis states, and this extends to a unitary operation for all of the 4 functions f. Okay, let's start by solving Deutsch's problem with these new classical queries. Here's a classical circuit for it. The first query XORs the value of f of 0 to the second bit. Then the first bit is flipped to 1, so the second query XORs the value of f of 1 to the second bit. At the end, the second bit contains the value of f of 0 XOR f of 1. This solves Deutsch's problem. Of course, it costs 2 queries. Can we do it with 1 query? We figured out that 1 query isn't enough with our original type of query. We need to be careful to check that our new definition of a classical query does not make it more powerful. To see why the new classical queries are not more powerful, note that if we're querying with input bits a and b, then we already know the values of those bits. And now there are only 2 possibilities for the output. The first possibility is that the output bits are a and b again, unchanged, which happens exactly in the case where f of a equals 0. The second possibility is that the second bit gets flipped in the case where f of a equals 1. So the only information about f acquired when such a query is made is the value of f of a. Therefore, even with this new classical query, the problem cannot be solved with one query. Now, here's a simple two-query quantum algorithm that also solves Deutsch's problem. It works in essentially the same way as the classical algorithm in terms of the computational basis states. But quantum circuits don't have to be restricted to these kinds of operations that keep things in computational basis states. Here's another quantum circuit that also solves Deutsch's problem, but with just one single query. We are going to investigate how this circuit works. But before that, let me comment that this algorithm is admittedly a curiosity rather than a practical algorithm. It's hard to think of a real-world application that fits this framework, and where the distinction between one query and two queries is also worth the trouble of building a quantum device. What you should pay attention to are the maneuvers that this algorithm makes. After this algorithm, we'll be seeing increasingly sophisticated extensions of these maneuvers that accomplish more dramatic algorithmic feats. Returning to this circuit, there are three Hadamard transforms, and each one plays a different role in the computation. Let's look at how each Hadamard contributes to the computation. First, there is the Hadamard applied to the second qubit in state ket1. Obviously, this creates the ket minus state. What's interesting about this state here is that it's an eigenvector of the poly x. Performing a bit flip causes the state to pick up a global phase of -1. Therefore, if the first qubit is in a computational basis state ket A, then the phase is -1 to the f at a. -1 to the f at a is a shorthand way of expressing +1 when f at a is 0 and -1 when f at a is 1. The 2-qubit output of the query is in state -1 to the f at a, ket A tensor ket minus. Notice that we could write the -1 to the f at a on the left side, since it doesn't really belong to a specific qubit. In fact, we can move it over to the first output qubit, like so. The 2-qubit output state is exactly the same. But this is a useful way of looking at what the query does when the second qubit is in state ket minus. That is, the first qubit picks up a phase of -1 to the f at a, and the second qubit doesn't change. We sometimes call this querying in the phase. At this point, you might wonder why we should care about this, since this is a global phase, and we know that global phases don't matter. But it's only a global phase if the first qubit is in a computational basis state of the form ket A. It's not a global phase if the first qubit is in superposition. This brings us to the role of the Hadamard applied to the first qubit that's in state ket 0. That causes the first input qubit to the query to be in an equally weighted superposition of ket 0 and ket 1, namely the ket plus state. Therefore, the state of the first output qubit after the query is in a superposition of ket 0 and ket 1 with respective phases -1 to the f at 0 and -1 to the f at 1. Let's look at what this state is for each of the 4 possible functions. For the function that's 0 everywhere, both phases are +1. For the function that's 1 everywhere, both phases are -1. This is the ket plus state, or minus the ket plus state. For the other 2 functions, where the 2 values are different, one phase is +1 and the other phase is -1. So, in that case, we have the ket minus state, or minus 1 times the ket minus state. Therefore, in the case where f of 0 equals f of 1, we have the ket plus state with a possible global phase. And in the case where f of 0 is not equal to f of 1, we have the ket minus state with a possible global phase. So all we need to do now is distinguish between the ket plus state and the ket minus state. This brings us to the third Hadamard transform, which does exactly that. After applying that third Hadamard transform, we measure in the computational basis and get the correct answer. To summarize the algorithm, the first Hadamard produces the ket minus, which causes f queries to induce phases. The second Hadamard causes the query to be in superposition, so the output of the query has a relative phase. And the third Hadamard extracts the phase differences from the state. This accomplishes something with one query that would require two classical queries by a classical method. Notice what this algorithm does not do. It does not somehow extract both values of the function f of 0 and f of 1 with one single query. In fact, if you run this algorithm, then you get no information about the value of f0 itself. Also, you get no information about the value of f1 itself. You just get information about the XOR of those two bits. Now, let's try to generalize this methodology to another problem. Let f be a function that takes 2 bits as input and produces 1 bit as output. Suppose that this function has the special property that it only attains the value 1 at exactly one of the 4 points in its domain. There are 4 possibilities for such a function, and here are their truth tables. The function can attain the value 1 at point 0, 0. It can attain the value 1 at point 0, 1, or at point 1, 0, or at point 1, 1. Now, suppose that you're given a black box computing such a function. You're promised that it's one of these 4, but you're not told which one. Your goal is to determine which of the 4 functions it is. First of all, how many classical queries do you need to do this? Please pause the video to think about this. The answer is 3 queries. You can query the first 3 places and see if one of them evaluates to 1. If none of them do, then by process of elimination, you can deduce that the 1 must be in the 4th place. Now, what about quantum queries? Let's try to find a good quantum algorithm for this. For functions mapping 2 bits to 1 bit, the queries look like this. There are 2 qubits for the input and a 3rd qubit for the output of the function. In the computational basis, the value of f of a1, a2 is XORed onto the 3rd qubit. Of course, that description is for states in the computational basis, but from that there is a unique unitary operation that matches this behavior on the computational basis states. Let's start along the lines that we did for Deutsch's algorithm. By setting the target qubit to state ket minus, so as to query in the phase, and then querying the inputs in a uniform superposition. Okay, what's the state just before the query is performed? You can pause to think about this. This is the state just before the query. Now, what's the state right after the query? Again, you can pause to think about this. Here's the state right after the query, with the appropriate relative phases. Now, let's look at what this state amounts to for the 4 different functions. For the first function, f sub 0, 0, that's 1 at point 0, 0, the state is this, with a minus sign for the ket 0, 0 term. For f sub 0, 1, the state is this. For f sub 1, 0, the state is this. And for f sub 1, 1, the state is this. Now, looking at these 4 states, what noteworthy property do they have? You can pause the video to think about this. They're orthogonal. If you take the dot product between any 2 of them, you get 2 positive terms and 2 negative terms, which cancel out. Since they're orthogonal, we can measure with respect to this basis. In other words, there exists a unitary operation U that maps these states to the computational basis states, and then we can measure in the computational basis. So this quantum circuit only makes one quantum query, and it correctly identifies the function among the 4. And as we noticed, this would require 3 classical queries. As an aside, a small challenge question is to give a quantum circuit with only Hadamard and C0 gates that computes this U. I'll leave this for you to consider. Is it possible to get a more dramatic quantum versus classical query separation than 1 versus 3? Next, we'll see a problem that a quantum algorithm solves with exponentially fewer queries than any classical algorithm. Let f be a function from n bits to 1 bit. We call such a function constant if either its value is 0 everywhere or its value is 1 everywhere. We call such a function balanced if its value is 0 in exactly the same number of places that its value is 1. There are 2 to the n possible inputs to such a function. Therefore, a balanced function takes value 0 in exactly 2 to the n minus 1 places, and it takes value 1 in exactly 2 to the n minus 1 places. Here are some examples of truth tables of functions for the n equals 3 case. The first 2 functions are the constant functions, the all 0 function and the all 1 function. The third function is a balanced function with all the zeros before all the ones. And the fourth function is another balanced function, but with the positions of the zeros and the ones mixed up. And the fifth function is neither constant nor balanced, just as a reminder that this third category exists. How many balanced functions are there? Lots. There are exponentially many such functions. For the constant versus balanced problem, we're given a black box computing a function that is promised to be either constant or balanced, but we're not told which one. Our goal is to figure out which of the 2 cases it is with as few queries to f as possible. First of all, how many queries do we need to solve this problem by a classical algorithm? You may pause the video to think about this. Okay, you probably realize that even if you query the function in many spots and always see the same value, you still might not know which way it goes. It could be constant, but it could also be that in many of the places that you did not query, the function takes the opposite value and it's balanced. It's only after you've queried in more than half of the spots that you can be sure about which case it is. Therefore, the number of queries that a classical algorithm must make scales proportionately to 2 to the n. That's a lot of queries for a large n. How many queries can a quantum algorithm get by with? In fact, it can be solved by a quantum algorithm that makes just one query. Okay, let's see how to solve this problem with a quantum algorithm. We'll start as usual, setting the target qubit to the state ket minus, and setting the other qubits, those where the inputs to F go, into a uniform superposition of all n qubit basis states. That's what applying a Hadamard to each of the n qubits in state ket 0 does. The state right after the query is a uniform superposition of all 2 to the n computational basis states of n qubits with a phase of -1 to the f at a for the ket a term. What does the state look like in the constant case? In that case, either all the phases are +1 or all the phases are -1. So the state remains in a uniform superposition of computational basis states and just picks up a global phase of +1 or -1. Now, what can we say about the state in the balanced case? There are lots of possibilities depending on which particular balance function it is. But one thing we can say is that the state is orthogonal to the case that arises in the constant case. Why? You might pause to think about this. In the computational basis, the state will have +1 in half of its components and -1 in the other half. So when you take the dot product with a vector that has, say, +1 in each component, you get an equal number of +1s and -1s, which cancel out, resulting in 0. One thing that we've seen a few times now is that when the cases that we're trying to distinguish result in orthogonal states, we're in good shape. Because being orthogonal means that, in principle, the states are perfectly distinguishable. Let's make things more explicit. Suppose that we now apply a Hadamard to each of the n qubits. In the constant case, this transforms the state to the ket all zeros state. In the balanced case, since unitary operations preserve orthogonality relations, the state is transformed to some state that is orthogonal to the ket all zeros state. We're ready to measure now. If the outcome is all zeros, then we report constant, and if the outcome is any string that's not all zeros, then we report balanced. Note that in the balanced case, it's impossible to get all zeros, because measuring a state orthogonal to the ket all zeros state cannot result in the all zeros outcome. That's how the one query algorithm for constant versus balanced works. It achieves something with one single query that requires exponentially many queries by a classical algorithm. Although everything I've said about the classical and quantum query cost for the constant versus balance problem is true, there's something unsatisfying about this separation. The classical query cost is expensive only if we require absolutely perfect performance. If a classical procedure queries f in random locations, then in the case of a balance function, it would have to be very unlucky to always draw the same bit value. Here's a classical probabilistic procedure that makes just 2 queries and performs fairly well. It selects 2 locations randomly, independently, and then outputs constant if the 2 bits are the same and balanced if the 2 bits are different. What happens if f is constant? In that case, the algorithm always succeeds. The 2 bits will always be the same. What happens if f is balanced? In that case, the algorithm succeeds with probability 1/2. The probability that the 2 bits will be different will be 1/2. By repeating the above procedure k times, we can make the error probability exponentially small with respect to k. Only 4 queries are needed to obtain success probability 3/4, and the success probability can be made to any constant arbitrarily close to 1 with a constant number of queries. In summary, we've considered 3 problems in the black box model. For each problem, a quantum algorithm solves it with just 1 query, but more queries are required by classical algorithms. For Deutsch's problem, any classical algorithm requires 2 queries. For the 1 out of 4 search problem, any classical algorithm requires 3 queries. And for the constant versus balanced problem, any classical algorithm requires exponentially many queries to solve the problem perfectly. However, there is a probabilistic classical algorithm that makes only a constant number of queries and solves the problem with bounded error probability. Along this line of thought, the following question seems natural. Is there a black box problem for which the quantum versus classical query cost separation is stronger? For example, for which even probabilistic classical algorithms with bounded error probability require exponentially more queries than a quantum algorithm? We'll address this question in the next lecture, and we'll end this lecture now.